which until recently had a substantial iron foundry and steelworks. The project brief was provided by the Tees Valley Combined Authority, supported by the Teesworks Heritage Task Force. The main aim of the project was to create an archaeological record of the site, buildings and plant prior to demolitions, and to use this record to create a public archive for public dissemination. The survey included a full survey of the principal buildings and plant at Redcar, South Bank and Lackenby sites. This included a level 2 record of the full site areas, a level 3 record of the Dorman Long Tower, Sinter Plant, Coke Ovens and the Lackenby Steelworks. There was also a level 4 record of the blast furnace at Redcar. The fieldwork was carried out over a period of 2 weeks. This was primarily a photographic record with approximately 2,400 photographs taken. In addition to the main survey, there was a requirement for gap analysis of public archives and museums and private collections. The entire project had a 4-month delivery schedule from inception to final report and archiving, so quite a quick turnaround. Okay, just to give a bit of historic context, and I want to avoid going into too much detail here, so I'm compressing about 200-year history into about 2 slides. The development of Middlesbrough from what was essentially a small hamlet of about 30 inhabitants into a major industrial centre began in the 1820s with the completion of the Stockton-Darlington Railway, which was followed by the formation of the Tees Coal Company, who sought to capitalise on the coal trade and available infrastructure. Iron manufacturing was established in the 1840s, and by the 1860s there were about 65 blast furnaces producing 2 million tonnes of raw iron annually. The Dorman Long Company was opened in the 1870s, opening new works and improving processes, and by 1914 was among Britain's largest producers. The first blast furnace at Redcar was completed by Dorman Long in 1917, and steel produced at Middlesbrough was used to build the Sydney Harbour Bridge and the Tyne Bridge. Following the end of the Second World War, there was a brief attempt at nationalisation of the steel industry, and the government made plans for investment which aimed to raise production in line with the anticipated rise in steel price. Sites were purchased at Lackenby to form an area of continuous development up to Redcar. The new Lackenby steel plant was commissioned in 1954. The Iron and Steel Act of 1967 transferred the 14 largest crude steel companies, including Dorman Long, to public ownership under British Steel Corporation. A 1973 white paper identified Teesside for new steelmaking complex and triggered stages of development at Redcar, which included a new blast furnace, coke ovens, power plant, etc., which I'll be talking about. The lighting of the blast furnace in 1979, which at that point was one of the largest furnaces in the world, marked the completion of the project. And again, to really simplify events, the sort of decades after that saw a general decline of the steel industry. The works changed management on a number of occasions, and the Steelworks Ironworks was eventually closed in 2015. Okay, so just to give an overview of the survey area, there's 3 main locations. Up here we've got the Redcar Ironworks or foundry. Down here we've got the Lackenby Steelworks, and over here is the South Bank. You can see we're dealing with quite a substantial area. It's about 4 kilometres between South Bank and Redcar, and the Steelworks itself is about just under 1 kilometre across. Okay, I'll just provide an overview of the Redcar area and the main areas and facilities, skipping over quite a few buildings and plant for time. The project was quite a rare opportunity to capture such a site, and as far as I know, it's one of the biggest projects of its type in terms of the scope of the building required, the building recording required. So Redcar is essentially the main iron smelting facility or foundry, and was at the north of the area. It was linked to the nearby steelworks by means of a dedicated rail link. Raw materials were processed and converted to molten iron in the blast furnace and then transported to the Boss plant to be converted to steel. The main facilities at Redcar included a wharf on the Tees estuary for raw materials handling facility, coke ovens for converting coal to coke, sinter plant, power station, stock house, blast furnace itself, and a whole range of supporting buildings and infrastructure. So we're just giving you a quick overview of the Redcar site, looking from around the area of the blast furnace across the power plant over here. We've got the blast furnace gas holder here, the byproducts plant gas holder, the coke ovens are sort of tucked away behind there. The byproducts plant, we can't really see it. There's also various chimneys and flare stacks, and all of this over here is essentially the raw materials handling area, and you can see how much pipe work and all sorts of things there is going across the site, and conveyors and all of that. So just to quickly touch on the raw materials handling, and starting in effect at the beginning of the entire process, the blast furnace and steel making sites operated continuously for campaigns lasting several years and outputted in the region of up to 11,000 tons of iron per day. Therefore, vast amounts of raw materials were required at the site, and these needed to be stored, sorted, weighed, screened, and distributed to the various plant needed. The RMH was the largest area of the Redcar site and had facilities for stocking and transportation of raw materials such as ore, coal, fluxes, lime, dolomite, bauxite, that kind of thing. The RMH wasn't a single plant, but rather a complex network of stock bunkers, crushers, weighing and blending hoppers, conveyors and junction houses. And the whole operation was overseen and controlled by from a central control room. Depending on the specification of the product required by the boss plant, the RMH would provide specific quantities of different materials. And this is kind of a schematic drawing that we did for the raw materials handling area, and it just sort of shows the extent of that process and showing how the material was distributed around the site. We've got stock beds and blending stocks. We've got weigh hoppers, bunkers, crushers and screening, and these are all connected together by this complex network of conveyors. Given the size of this, rather than focusing on every individual recording every individual part of this site, we try to get a general overview with examples just to sort of capture that process. So the sinter plant was essentially one of the biggest structures at Redcar, with maybe this section of the blast furnace itself. The sinter plant processed raw materials and used these to create nodules, sinter of a consistent size and composition. This was a really important part of this process, with the sinter forming about 80% of the blast furnace burden, and it had to have the correct chemical composition, be free from dust, and be strong enough to withstand the burden weight of the furnace. It was commissioned in February 1978 and was the first part of the site to come into use, and until the completion of the blast furnace, it provided sinter for the nearby Cleveland works. A similar plant was also erected at Port Talbot, and various alterations and improvements for efficiency were carried out over its lifetime. So this is a sort of schematic plan of the sinter. It's basically an extensive facility, highly automated, interconnected areas with a continuous process of blending and mixing of materials and waste being constantly collected for reuse. The main processes really are raw materials preparation. We've got an automated system of storage bins and hoppers which proportion and mix the materials needed. There's mixing and granulations, where the blend is mixed to create the granules that go onto the sinter strand. The sinter strand is this 185-meter continuously moving strand. At the top end of it, there's a furnace, and the prepared mix is dropped onto there, passes through the furnace, where blast furnace gas is used to ignite the top layer. And once lit, it relies on coke breeze to sustain the combustion. Upon reaching the end of the strand, it drops through a sinter breaker into this annular cooler, where for about 25 minutes it's cooled down. In the sintering process itself, there's a great big fan house at the end, and the suction fans draw air down through the sinter bed, which partially melts and fuses the material to create the sinter. Once the sinter is cooled, it's then crushed and screened to the required size, and any dust is kind of returned back into the process to be reused, and the sinter passes through all the screening plants, goes along the conveyor out to the junction houses and onto the stock house. The waste gases are then collected, cleaned from dust, passed through electrostatic precipitators and various dedusters and scrubbers before being released. A couple of views of the sinter plant. Here we can see the annular cooler at the west end of the sinter plant. There's a conveyor going up to the top there, bringing the raw materials up to the storage bins. Here we're looking down below the strand. We can see high pressure locks which are connected to the waste gas pipes above us. These work as part of the dust collection system. This is a view of the sinter bed looking down towards the furnace. These are the electrostatic precipitators. You can see the scale of them just based on these little steps over here. And this is part of the dust collection facility over there. So these are just two of the examples of the types of drawings that were available to us, accessed via an internal company filing system. And this is a sort of level of complexity of the drawings that we had. Moving on to the coke ovens. There were two batteries at Redcar, each about 300 meters in length, dating from the 1970s. There are also batteries at the South Bank site dating from the 1950s. These have been partially demolished by the time we got to site. Coke ovens are a very important part of the process. What they do is they bake crushed coal at high temperatures in a low oxygen kiln to produce coke. The baking process removes impurities and separates the volatile byproducts. The waste gases contain a useful and valuable mix of byproducts such as tar, ammonia and benzol. And these are collected and processed in the adjacent byproducts plant. A coke oven is essentially a series of narrow, tall coking chambers lined with refractory bricks and sealed with doors. There's also conveyors, stock bunkers, preheaters, stacks and quench towers. This is actually an image of the South Bank coke ovens. Here we see the coal bunker in the middle, the charging car, which distributes coal into the individual ovens. And we're also catching the pushing stage process where the coke is being pushed through the kiln, through a guide car and down into the quenching car to be transported over here to be cooled. Just to give you an overview of the coking process, the main stages really. The initial stage is what's called the charging stage. So coal is moved up conveyor into the stock bunker, located centrally to the batteries where it's preheated. The coal is then dropped into a charge car, which traverses the roof of the kilns and deposits the coal into each kiln. Then we've got the carbonisation stage. Each kiln has flues built into the wall of the ovens, and burning gas is heated in those flues to heat up the bricks in the wall. The heat is transferred through the coal by conduction from the oven walls, causes them to bake but not to burn at very high temperatures. The carbonisation cycle takes about 18 hours per kiln, and when that's completed, we arrive at the coke stage, the coke pushing stage. At the completion of the cycle, a guide car, pusher car and quench car are manually manoeuvred into position at the correct kiln door. They open the door and the ram pushes the hot coke through the kiln, out through the guide car and into this sort of locomotive, which is a quench car, where it's taken to be cooled and put onto a conveyor. So this is just a view of some of the kiln doors. You can see they're very narrow, quite tall. We've got a gas pipe going over the top of them. This over here is one of the charge cars. It has these little storage sort of bins on the top of it, and they deposit the coal into each kiln. These massive things over here, you can see the size of the Harris fencing. These are the pusher cars and rams, and they just push the coke through the kiln. And here again, we can see a guide car, which guides the hot coke into this little locomotive there. Okay, we had a massive power plant at the site, the main purpose of which was to provide a steady supply of high pressure cold blast air into the stoves at the blast furnace. This was essentially a single large building and included a huge turbine hall, water treatment plant and pumps, boilers and an office block with a control room which was isolated from the main working areas. The building was quite large, measuring about 88 meters by 83 meters. And in common with most other buildings on the site, it was essentially portal-framed steel structure, simply clad in steel sheets with some brickwork at the lower levels. The only windows really were to the sort of office block in the corner. So the blast furnace and coke ovens produced huge amounts of waste gas, and for cost offsetting, it was important for this to be reused, including in the blast furnace stoves. A large amount of gas was available to burn in the three boilers. These produced about 500 tons high-pressure steam per hour, and this was used by the two turbo blowers to send high-pressure cold blast to the stoves, and also to generate electricity via the 6 turbines. The power was used throughout the steelworks and ironworks, and the power plant was also connected to the main grid. The water treatment plant produced high-quality feed water to supply the boilers. It received raw water and potable water, which was subject to cleaning, filtration, and treatment through an automated process. Sadly, we didn't actually have a lot of time spend in the power plant, so we had to do a fairly rapid survey, which was a bit unfortunate for us. Moving on to the main blast furnace itself, which is, I guess, the bit that everyone recognises. Here we can see all the gantries and platforms which surround the furnace, which you can't really ever see. And in front of it here are the stoves, great big conveyor moving up to the top. There's various adjacent buildings which include control rooms and workshops. This formed the visual focal point for the Redcar site, being its most prominent structure, standing to a height of about 104 meters, which is about the height of the top of St. Paul's and just about the height of a Saturn V rocket. Built in 1979, it was at the time the largest in Europe, I believe. This was also the main focal point for the iron smelting, where all the raw materials from the preceding stages, such as coke and sinter, were brought together. The main function really was to produce molten iron to a specific tonnage and quality as required at the Boss plant, something in the region of 11,000 tons per day. The first campaign ran between 1979 and 1986, when it produced about 15 million tons, operating continuously. It was then relined and the coke ovens were rebuilt, and a second campaign ran from 1986 to 2000, producing about 43 million tons. There was a third campaign between 2000 and 2011, and a final campaign between 2012 and 2015, when the whole site was shut down. Here we're looking at the rear side of the blast furnace. You can see the two cast houses. These are the waste gas pipes with a downcomer pipe which brings the waste gas down to the dedusters and scrubbers where the gas is cleaned for reuse. At the very top is the bleeder platform, and that's a great big crane. So this is just a quick plan of the blast furnace itself. So surrounding the furnace, there's a sprawling complex of associated infrastructure, including dust and gas collection, cleaning and processing, and all sorts of conveyors for slag and waste. Here we see the actual furnace at the heart of the blast furnace complex, with cast houses on either side, with channels leading out to rocker spouts where torpedo ladles sit on these railway tracks. There's slag pits to either side. Over here we can see the stoves, and on this side really it's sort of treatment for gas and water. So a section through the blast furnace. The main parts really are the 42-meter tall furnace with a 14-meter diameter half. We've got a raw materials conveyor. Up here is a Polworth hopper which charges the furnace. We've got 4 external combustion chamber stoves which aren't on this image. We've got the 2 cast houses to either side. This is the cast house floor, bustle pipe and tuya platforms, and these are the torpedo ladles which would catch the molten iron. Essentially the process really is that the raw materials are brought up, dropped into the conveyor and charged in layers into the furnace. Hot gas is hot air is brought in through the bustle pipe and forced into the through the base of the furnace. At intervals, the iron is tapped out and it comes out in the cast house floor and drops down into the torpedo ladles there. So these are the 4 stoves located externally to the blast furnace. These provided preheated air for the furnace. They're cylindrical structures filled with refractory bricks. The stoves used recovered blast furnace gas as fuel for cost efficiency. The gas is burned in the burner chamber, and the hot gas is drawn through and heats up the bricks in the checker chamber. The cold blast arrives from the power plant, and it rises through the hot bricks, where it's heated up to a very high temperature, and once it's required, it passes out through the hot blast and into the furnace. So over here we can see, looking down onto the top of these things, and they really are huge. When you're standing on top of them, they're absolutely massive. So here we're moving into the furnace area. What we're looking at here is the tuya platform. The hot blast from the stoves is carried via this massive bustle pipe to the furnace, and it's forced under high pressure through these tuya nozzles just above the hearth. The hot air combusts the coke, which produces superheated carbon monoxide, which rises through the charge layers, melts the iron ore, which in turn percolates downwards through the furnace. You can see here the sheer size of this. As this gentleman here, the hot air pipe comes through. These are some of the spare tuya nozzles. So we're looking now in one of the cast houses. The platform that we were just looking at is sort of up above there. This is essentially where the iron is tapped. The main body of the furnace is kind of up here, and there isn't really any way that you can actually see it from site because it's always surrounded by various pipes and other equipment and structures. So at intervals, the molten iron was tapped from the base of the furnace. Here's quite an old picture. I assume health and safety has moved on from suits and hats. There were 2 tap holes in each cast house, and in a modern blast furnace there are clay guns which inject a plug of clay into the tap hole at the end of each cast. When it comes time to casting, a drill is moved into position. This basically drills through the clay plug, and the iron and slag flows out into these channels in the cast house floor. I believe the output was around 12 casts per day. The molten iron flows down these channels and drops down into rocker spouts and into torpedo ladles, where it's transported across to the steelworks. Throughout the process, the waste gases are continuously being collected and processed through scrubbers and dust extraction to produce clean blast furnace gas for reuse, and the dust is then reused back into the sinter plant. Just a couple of views really of within the blast furnace area. This is one of the control rooms. As you can see, it's a lot of computerization by the time the later campaigns are happening. These here we're near the top of the blast furnace. That's the bleeder platform. The waste gas pipes coming off, and the downcomer taking it down towards the cleaners. Here we're looking down from the same level onto the charger and the hopper. And this is the bottom of the Polworth hopper, which basically allows for continuous and controlled loading of raw materials into the furnace. Moving on to the Dorman Long Tower. This was at the South Bank site. Essentially, it's a massive 5,000-ton coal bunker built in the 50s and sits alongside 2 coke oven batteries. One of which had been demolished prior to our survey. It's about 58 meters tall, built of reinforced concrete. It does face towards a railway, and so it did actually have some emphasis on architectural aesthetics in a very sort of brutalist kind of manner. Quite a distinctive structure. It was briefly granted Grade 2 status as a sort of recognised example of early brutalist architecture. This was subsequently somewhat controversially revoked, and the building was demolished shortly after we finished our recording. Quite an unsafe structure, so there was very little access around and inside it, apart from maybe a little lobby area. The requirement was for a level 3 survey. Fortunately, there was quite a good archive of historic photographs showing it in its original setting. And also one quite detailed cross-section of it, which we were quite fortunate to find. Here's a view of it sort of at the time when we came. This is basically where the roof of the coke ovens would have been, with some locomotives still in place, and you can just about see how the pusher car and the guide car would have sat in relation to this. Moving on to the Lackenby site, this is where the basic oxygen steelmaking took place. It received molten pig iron produced at the Redcar blast furnace and essentially converted that to high quality steel. The liquid steel was then sent to the adjacent continuous casting or concast plant for slab and boom production. It was intended to produce about 60,000 tons per week of liquid steel, the majority of which was sent for continuous casting, and 17% as ingots. As you can see, it's basically a massive steel frame building, in places up to around 700 meters long, comprising adjoining portal-framed bays of various heights, lengths, and widths, with the steelmaking process going from bay to bay. An irregular, quite asymmetrical arrangement of blocks, purely functional, to allow for efficient internal processes and materials movement, with very little consideration, if at all, really, for architectural and aesthetic design. So this is a plan of the steelworks area. As I mentioned, it's anywhere up to 500 to 700 meters, depending on which bay you're looking at. With a series of adjoining bays, which allow the process to move sort of safely and efficiently from the start of the process through down into the final casting. And you can see here, get an approximate idea of how big some of these places were, because they're absolutely enormous when you're walking around them. Very easy to get lost when you don't know your way around. So just give you an idea of the sort of boss process. Basic oxygen steelmaking is the main steelmaking method, where a charge of carbon-rich pig iron from the blast furnace is refined into steel using oxygen. The process lowers the carbon content and removes impurities. The first stage really is charging. The molten iron is delivered by rail and tipped into a 200-ton ladle and carried to converter vessels, such as that one there. The bus plant had 3 250-ton capacity converter vessels. These are tilted forwards and charged with scrap metal, which helps to control the temperature during oxidizing reactions. An overhead crane carries the ladle in, and the molten iron is poured into the converter, which is then returned back up to upright position. Then we've got oxygen blowing. Water-cooled oxygen lances are lowered into the vessel and blow pure oxygen at very high pressure, which raises the temperature of the iron and initiates exothermic reactions and oxidizes the impurities. During this process, various fluxes are added, which combine with the impurities to form slag, which can be removed. After about 50 minutes, the furnace is tilted and the molten steel is poured into a ladle. Then we come to the refining process, where the quality and composition of the steel can be precisely adjusted to exact requirements at various sort of flushing and degassing stations, depending on the exact specification of what product you're looking to produce. So again, we're very fortunate to have these quite detailed drawings for this area, and it shows really very nicely how these bays work. So here is the converter vessel. This is a scrap metal car, and this is one of the ladles which will be brought in, tipped into the converter, and then it'll move into this area where it's going to undergo various refining. This is the tallest bay, about 70 meters high, and this photograph here is essentially showing, I think we're probably about there in terms of height, that we're looking onto the top of the converter vessels with the gas extraction hoods and oxygen lances. This is one of my personal favorite photos that I took during the whole process. I think this is the ladle bay. You can see just about here overhead cranes which traverse the length of this bay. We've got ladle dryers over here. I think these are argon stirring lances. As you can see, massive open height spaces, very long. And yeah, you would have had hot ladles moving through here. This is another bay. I think this is a teeming bay. There's a tank degasser, which is part of the final refining process. And over here, you can just about see these are massive lumps of solidified iron left over from some of the ladles. Moving on to the continuous casting or concast process. Basically, this converts the molten steel from the previous stages into semi-finished products such as slabs, blooms, and billets. Following the refining and alloying, the molten steel is transferred from ladles into a tundish, which is basically an intermediate vessel that controls flow rate. Molten steel flows out through a tundish. You can see the process here. Passes through a mold and a spray chamber where it starts to cool and solidify. The emerging strand passes through straighteners and it's cut to the required sizes and lengths, creating slabs, blooms, billets, which can be sent to the hot rolling mills or stored for later processing. Over here, some of these are quite useful. We found them in company newsletters, sort of flow process diagrams, really useful for helping us understand the process. Just a couple of pictures. This is one of the tundish vessels. Over here, this is the, what are we looking at? Slab straighteners and the runout. So these are some of the straightener segments. I think over here, this is the mold bay, which is an adjacent bay as part of the concast process. Again, very, very, very big spaces with a huge amount of equipment in them. Okay, this is a view of one of the ladle cars. So we're back right at the top of the concast process. So the hot ladles, the ladles full of the molten steel, they'll be dropped in the ladle car. And these would move into the exact position to align with the tundish and the mold. And the steel would flow out through the bottom of the tundish vessel, through the mold, and then carrying on through the casting process. So yeah, just to get through, I guess, some of the challenges and opportunities. I guess to start with just the framing and scope of the project, which was set out as a competitive tender with a given budget, time frame, and a brief for deliverables, which obviously sets constraints for budgetary resourcing and focus for the program. 17-week program for setup, survey, and reporting. Unfortunately, the survey time coincided with the beginning of demolition works and CDM regulations. So we basically set aside about 2 weeks for the on-site surveys. We're also required to undertake a review of all potential archive searches as part of a gap analysis. And we did quite a thorough archiving review, as well as to support the actual reporting. The level of detail required was quite a major challenge given the constraints on site and the time and lack of information on what drawings would be available, especially the level 4 requirement for the blast furnace, which we had much discussion over at the quotation stage as to how we'd fulfill that. We were able to do a quick tour of the site at the quotation stage, which really helped us to understand the practicalities of the site. Our submission basically formed a method statement with a detailed program for key deliverables and schedule for updates. This also allowed us to define our own parameters and expectations for delivery and what we needed to fulfill the brief. We had regular telephone, email updates, and bi-weekly Teams meetings with the client team. We realised really at the outset that the main interest wasn't necessarily in the architecture of the structures themselves, but rather the processes and the functional relationships of the plant, how the materials moved around the site, how these were changed and transferred back and forth as product or waste. And we therefore tied the level of recording to the importance of each part of the works. And that's how we provided the detail in the project. It reflects that relative significance within the overall process. By the way, this is the bleeder platform at the very top of the blast furnace. So great view from up there. Bit of a scary process to get up there. For the site visit itself being the real critical factor and with a very short deadline, essentially there were 16 main areas to be recorded, and our program clearly identified the order that we would approach these during that period. This really allowed for no more than a single day for even the largest and most important of the buildings, and we basically had to do many parts of the site in the single day to stay on schedule. The site itself is very large and requires a lot of time just to move around between the different areas and even just within the structures themselves. Under normal circumstances, for recording, you normally do a walk around of a building to familiarize yourself, note features of interest, and figure out how you're going to go about the survey. In this case, however, our recording for each part of the site was basically a single guided walkthrough with very little chance to familiarize yourself ahead of time. A lot of access restrictions due to unsafe structures and a lot of other hazards. Very little opportunity for artificial lighting or flashes, either due to lack of power or just simply the scale of the buildings makes flashes kind of useless. Not much room for tripods either, because of the tight spaces, awkward access, the need to use gantries and external stairs, and also just very little time to set up for tripods. So we basically relied on handheld photography with high ISOs, leaning on rails and conducting general kind of acrobatics to get the shots we needed. Big challenge just to capture the buildings in their entirety due to their massive size, and in places we're just not able to get far enough from them to take clear views of the structures. Once the demolition process started, this kind of did open up a few areas, so we were able to go back and do some of that, or we were able to plan ahead and take some of our photographs from other nearby buildings that we were going to be doing, for example, the next day. So yeah, quite a big challenge just to make sure that we managed to capture all the details of the building, the form and construction phases of development, all the important plan, and the way that the plant sort of processes interacted with each other and how they were controlled. And maybe I shouldn't admit this as a buildings archaeologist, but I mean, a massive challenge is just familiarizing yourself in the first place with such a specialist subject. It required a lot of research at the outset. We get used to sort of looking at houses, nice architecture, timber framing, barns and stables, but this kind of project requires a very different mindset and knowledge base, and it's obviously not something that crosses our desks very often. But from my own point of view, and from my experience of recording, the site constraints force a level of adaptability and focus. You're forced to prioritize the most important elements in the back of your mind, how these are going to form the basis of the report, and how you're going to describe how all of these areas are going to fit in with your description of the process, rather than just a dry description of buildings. As I mentioned, we didn't have any digitized CAD drawings, but a very large resource of scanned technical drawings, which weren't necessarily well organized or catalogued. This was quite a time-consuming process to review, but it did provide a lot of detail and a basis to produce figures for the report. The most important resource really was the site staff, who, despite the works being decommissioned, many of which were still there, they served as our guides during the walkthrough, and we arranged for sit-down interviews with managers and key staff plant. This allowed discussions of the processes. It confirmed the technical language and terminology, and really allowed a much needed level of detail and authenticity to come through in the report. We were also able to contact them during the reporting stage, which is really important for accuracy. There's also several decades worth of company newsletters at the archive, which provide a huge amount of information and technical background and historical background as well. On site in the offices, there's a massive collection of technical documents just sitting in huge boxes, unsorted and uncatalogued, which were very time consuming to go through, but quite useful. Although we did have to simplify a lot of the information for our report. There's also staff training manuals, induction training presentations, which provided really clear outlines of processes in the buildings. Some of the areas on site had plans and displays. We were fortunately able to undertake a small number of follow-up visits, mostly focusing on the Steelworks area, which I simply just ran out of time to on the one day I had to really do it justice. So I managed to come back and do some more visits, but I also took the opportunity to hop across to Redcar and take a few more photos. The final report is quite a big document, about 300 pages, about 350,000 words, with about 380 plates. And I was amazed that I received quite a relatively few corrections and amendments. Only required 2 stages of reissue. Massive digital archive of about 2,300 images was submitted to the Middlesbrough archive, and the report and plates were then submitted to ADS. Hopefully I'm in time, and there's a bit time for questions, so I'll hand back over to the floor, and thank you for listening.